So today we are going to discuss the problem on harmonic oscillator. So harmonic oscillator problem can be solved with the help of the Hamilton-Jacobi theory. So this Jacobi theory can be applied for solving the motion of a one-dimensional harmonic oscillator. We know that the Hamiltonian of the system is H is equal to 1 by 2m into p square plus half kq square equal to total energy E. Here p represents the generalized momentum, m is the mass and q is the generalized coordinate. This is equal to E represents the total energy, and omega square is equal to k by m, where k is a constant. But the generalized momentum p is equal to dou s by dou q. That is, by differentiating the principal function s partially with respect to the generalized coordinate q, we get the generalized momentum p. Now we know that the Hamiltonian equation is h is a function of q1, q2, q3, qn, comma dou s by dou q1, dou s by dou q2 plus dou s by dou qn, comma t plus dou s by dou t equal to 0. Now here q1, q2, q3, qn are represents the generalized coordinates, and now this can be written in the form 1 by 2m into dou s by dou q whole square plus half kq square plus dou s by dou t equal to 0. Name this equation as 2. Actually what we have done, the h is replaced by 1 by 2m p square plus half kq square in the above Hamiltonian equation. Now this principal function has t as the explicit variable only in the last term, that is in dou s by dou t we see that t is the explicit variable, and therefore the solution of the principal function s can be written in the form s is a function of q alpha t equal to w of q alpha minus alpha t, where s is the principal function of the Hamiltonian and w of q alpha is the Hamiltonian characteristic function, where alpha is the constant of integration. Now differentiating the principal function S partially with respect to q and also partially with respect to t, we get dou s by dou q equal to w is a function of q, so therefore dou w by dou q, and also we differentiate s partially with respect to t, so dou s by dou t we will get minus alpha into, while we are differentiating t we will get 1, w in the term w t is absent, therefore while we are differentiating partially with respect to it we will get 0 as answer. So name this equation as 4. Now substituting these values in the equation 2, 1 by 2m into dou w by dou q whole square plus half kq square minus alpha equal to 0, we get here the previous equation. In the equation 2, 1 by 2m into dou s by dou q is replaced by dou w by dou q, half kq square you write as it is, and instead of dou s by dou t we can write minus alpha in the equation 2. So therefore we will get 1 by 2m into dou w by dou q whole square plus half kq square is equal to alpha. Now the left hand side of this equation is Hamiltonian. The constant alpha is the total energy E of the system. So therefore the equation 5 can be written in the form 1 by 2m into dou w by dou q whole square is equal to alpha minus half kq square. Now here from which we can find the value of, you take dou w by dou q whole square is equal to take 2m to the right hand side, 2m into, take LCM 2 alpha minus kq square by 2, and we find the value of dou w by dou q, that is equal to root of 2m alpha minus mk square. Now from which we can find the value of dw. dw is nothing but root of 2m alpha minus mkq square into dq. You take 2m alpha, root of 2m alpha outside, then we will get dw equal to root of 2m alpha into root of 1 minus kq square by 2 alpha into dq. Now integrating, we get, you take root of 2m alpha outside, so w equal to root of 2m alpha into integral root of 1 minus kq square by 2 alpha into dq. Now we have found out the value of the Hamilton characteristic function w. Now substitute the value of w in the equation 3. We get s is equal to root of 2m alpha into integral root of 1 minus kq square by 2 alpha dq minus alpha t. Here in the C equation, w q alpha, in the third equation you get s of q alpha t equal to w of q alpha minus alpha t. In this equation, we replace the w q alpha by the found out answer. So name this equation as 7. But we know that the constant beta is obtained by differentiating s partially with respect to alpha. So from which we get beta is equal to dou s by dou alpha. You differentiate s partially with respect to alpha. Here s is equal to root of 2 alpha into integral root of 1 minus kq square by 2 alpha dq minus alpha t. Now we applying the product rule, we get first root of 2m into, when root alpha is differentiated we will get 1 by 2 root alpha, and take the other term as it is, integral root of 1 minus kq square by 2 alpha into dq, and plus you take root of 2m alpha out as it is, and while we are integrating root value 1 by 2 root of 1 minus kq square by 2 alpha, and then term inside the square root is to be differentiated partially with respect to alpha. When 1 by alpha is differentiated, we will get minus 1 by alpha square. So therefore kq square by 2 alpha square will be in the numerator. And in the terms, you take root of m by 2 alpha outside, we will get in the first term integral root of 1 minus kq square by 2 alpha plus root of 2m alpha into, so making adjustment kq square by from the term kq square by 2 alpha square, you bring 1 alpha to the denominator, root of 2m alpha divided by 2 alpha. We will get in the integration part kq square by 2 alpha divided by root of 1 minus kq square by 2 alpha dq minus dt. From the two terms, take root of m by 2 alpha outside, you will get 1 minus k square 1 minus kq square by 2 alpha plus kq square by 2 alpha divided by root of 1 minus kq square by 2 alpha dq minus dt. And the two terms kq minus kq square by 2 alpha plus kq square by 2 alpha get cancelled. You will get integral dq divided by root of 1 minus kq square by 2 alpha minus dt. This is the value of beta. You bring t to the left hand side, so t plus beta is equal to integral root of m by 2 alpha into integral dq divided by root of 1 minus k into that can be written as root of q into root of k by 2 alpha the whole square. We know that the formula, integration formula, so sin inverse of x by a. So now here x is nothing but q into root of k by 2 alpha. You write sin inverse of q into root of k by 2 alpha divided by, we are differentiating and then we take the constant is root of k by 2 alpha, we write in the denominator, and then in the numerator you are on the outside root of 2m by alpha, root of m by 2 alpha is there. So now on simplification, root of m by 2 alpha divided by root of k by 2 alpha, you will get root of m by k into sin inverse of q by q into root of k by 2 alpha. This is the value of t plus beta. But we know that the value of k is equal to m into omega square. Initially we have assumed it. So therefore replace k by m omega square in the equation 8. We will get root of m divided by m into omega square, sin inverse of q into root of m omega square, root of m omega square by 2 alpha. Now by cancelling m and taking on the omega square from the square root 1 by omega into sin inverse of q into root of m by m omega square by 2 alpha. So t plus beta is equal to from by simplification we can find the value of q. Q is equal to root of 2 alpha divided by m omega square into sin omega of t plus beta. Name this equation as 9. Now you differentiate this term t with respect to t, we will get q dot equal to root of 2 alpha by m omega square into, when sin omega t differentiated, cos of omega into t plus beta. When omega into t plus beta is differentiated with respect to t, you will get omega. So the final answer will be root of 2 alpha by m into m, the term inside the m square root m omega square, and outside the term omega will get cancelled. So we will get the value of q dot is equal to root of 2 alpha by m into cos of omega into t plus beta. Now therefore the momentum is obtained by applying the formula small p is equal to mass into q dot velocity. Now we have found out the generalized velocity value q dot s root of 2 alpha by m into cos of omega t plus beta. Substitute in the q dot value, and then on cancelling you will get p is equal to root of 2m alpha into cos omega of t plus beta. Now we have found out the generalized momentum p. Now the constant values alpha and beta are the related to the initial values, namely q naught and p naught. Suppose the particle is at rest at the starting time t equal to 0, generalized momentum p equal to p naught, and the particle is displaced from the position q naught. Now from the equations 9 and 10, we find the value of sin omega of t plus beta and cos omega of t plus beta, and squaring and adding we will get the term as m omega square q square by 2 alpha plus p square by 2m alpha is equal to 1. Now in this equation we substitute the initial condition p equal to p naught and q equal to q naught. We will get so q naught square m omega square by 2 alpha will be equivalent to 1. Now from this we can find the value of alpha, and it is equal to q naught square m omega square by 2. Now from the equation 9 we will get q naught equal to q and t equal to 0. Substituting we will get here the ninth equation is q equal to root of 2 alpha by m omega square into sin omega of t plus beta. In this equation you replace q by q naught and t equal to 0. So therefore you are getting the value of q naught equal to root of 2 alpha by m omega square into sin omega beta. Now substitute the value of alpha from the equation 11. You will get q naught equal to root of 2 by m omega square into alpha is replaced by q naught square m omega square by 2 into sin omega beta. Now 2 get cancelled, m omega square will get cancelled. So square root of q naught square will become q naught and q naught into sin omega beta. Now from this we can find the value of sin omega beta equal to 1, and this is imply omega beta equal to pi by 2. From this we can find the beta equal to pi by 2 omega. Now from the equation 5, 1 by 2m into dou w by dou q whole square plus half kq square is equal to alpha. Now the constant alpha can be identified as the total energy E. Also from the equation dou S by dou T plus H is equal to 0. Now the system is conservative from the equation. So therefore you will get alpha equal to H is equal to E. Hamiltonian is equivalent to the kinetic energy, total energy E, and this is equivalent to the constant alpha. Thus the Hamilton's principal function S is the generator of a canonical transformation to a new coordinate that measures the plane angle, phase angle of the variation, and to a new canonical momentum alpha identified as the total energy. The meaning of the last paragraph is we have found out a new canonical momentum alpha and that is equivalent to the total energy. Canonical momentum, since it is equivalent to H, it is canonical momentum. So here we have obtained from the equation alpha equal to H equal to E. And also for another new coordinate Q, so with the help of that Q we can find the phase angle beta. That beta is calculated by pi by 2 omega, and it is given in the equation 12. So this is the result. Harmonic oscillator problem. From the harmonic oscillator problem we have found out the constants alpha and beta. Thank you.